everyone, my name's Logan and welcome back to the lecture hall. For today's video, we are covering section 7.2, Trigonometric Integrals. So, let's begin. If we had the integral cosine cubed dx, how do we solve that? Well, we know what the integral, or the antiderivative I should say, of cosine is. It's, well, sine. But we would run into some chain rule issues with, since this is a power, we'd have a power rule and then there's a function inside of it. So we run into some issues because if we did a u substitution with cosine, we would not have our du to properly do it. But we do know one thing. We know that sine squared plus cosine squared equals 1. And that's the same thing as saying cosine squared minus, or 1 minus cosine squared is equal to sine squared. So, what can we do? Well, we can rewrite this integral cosine x dx equal to the integral of 1 minus sine squared x cosine x dx. And then we see, like, oh wait, well, we know how to do this one, do we? Well, let's see. Well, if we just distribute this cosine, this would be cosine minus sine squared x cosine. And if we integrate with, do a u substitution with our u equal to sine, well, our du would be equal to cosine x dx. So we could say, well, this is equal to cosine x minus sine squared x cosine x dx. And, well, we know the integral of cosine, sine, so that'd be sine x, and then we'd minus, well, we know the integral of sine is going to be, or we know, well, if we do a u substitution here, we say u equals sine x, and then du equals cosine x dx. Well, this would turn into u squared du, and while this sine squared turns into u squared, well, the integral of u squared is going to be integral u squared du is equal to 1/3 u cubed. Well, then this is just over 3 cubed of u, so sine cubed x. And then we see, okay, well, that's our integral. Are we done? No. Plus c, this is an indefinite integral. We don't know what possible constant could have been taken away when we did the integration in the first place. So this is going to be a lot of the video. We are renaming our sines as cosines and cosines as sines. Now, what are the rules for this? Well, let's get into it for sine and cosine integrals. So if we had the general form, the integral of sine to the mx times cosine to the nx dx, well, we need to know a general convention for how to do this. Well, if m is odd, i.e. m equals 2k plus 1 for any k in z, as in k where k is an integer, any odd number, well, we can rewrite this as the integral of sine to the 2k plus 1x times cosine to the nx dx, which we can then rewrite as the integral of 1 minus cosine squared x to the k power times cosine to the m times sine x dx. And then from there, we use u equal to cosine x, because then du would be equal to negative sine x dx, and then the integration would be very, very easy from there. Same sort of deal now, if n is odd, i.e. the power over cosine is equal to 2k plus 1, where k is in z, we can rewrite this as the integral of sine to the mx times cosine to the k plus 1 x dx, and we can rewrite that as the integral of sine to the mx minus 1 times 1 minus sine squared x to the k power, and then we bring a sine x out and do, that's a lie, not a sine, a cosine x out. And we would then use u equal to sine x, and then our du would then be equal to cosine x dx. And with that, we would be able to integrate them using a u substitution, and we would get it perfect. But what if, instead of them being odd, what would we have to do if both powers were even? Because if both powers are odd, we can just choose to do one of them and it'll still work. But if none of them are odd, i.e. both of them are even, what do we have to use? Well, we have these things called the half-angle formulas. And so if both are odd, or both are even, we need to use the half-angle powers, and that's essentially, this is sine squared x is equal to 1/2 1 minus cosine 2x times, so that sine squared x is equal to 1/2 minus, or 1/2 times 1 minus cosine 2x, and then we have cosine squared x is equal to 1/2 1 plus cosine 2x. And so we use these when m and n are even. And from there, we'd be able to break it into something smaller. We may be able to find an even power if maybe this was sine to the 6th. Well, that's sine squared cubed. And then we may have something we can work with when we have powers that we want, because when we can do the substitutions when they're even. And one final note that might be helpful is we know that sine x times cosine x is equal to 1/2 sine to the 2x. So if we just had maybe just the integral of sine x cosine x, or maybe sine squared cosine squared x, or something like that, we could rewrite it in terms of 1/2 sine 2x, and that could be very easy to use. Now, what if we had something with tangents and secants? Because we've covered 2 of our trig functions, and then now we have 6, and so we now have to look at tangents and secants. Cotangents and cosecants follow suit with the same thing for tangents and secants. So, well, what do we know? We want to find the integral of tan to the 5th theta secant squared theta d theta. And we know that the derivative of secant is equal to secant tangent. Well, that's all well and good, but what else do we know? We know sine squared theta plus cosine squared theta is equal to 1. If we divided by cosine squared theta on both sides, cosine squared theta, we would have that tan squared theta plus 1 is equal to secant squared theta. And so with that, we can also say that tangent squared theta is equal to secant squared theta minus 1. And so now we can see that if we had derived based off secant, we pull out a secant and a tangent outside, we could do a substitution such that our u is equal to secant theta, and then our du would be equal to secant theta tan theta. Well, we could rewrite this as the integral of tan to the 4th theta secant theta times secant theta tan theta d theta. Next, we can convert this tangent into secants, because we can say tan squared theta is equal to secant squared theta minus 1. So we can rewrite this as the integral of secant squared theta minus 1 squared times secant theta times secant theta tan theta d theta. And then if we do a u substitution, our u substitution would be u is equal to secant theta. Well, du would be equal to secant theta tan theta. Well, this is just then equal to the integral of u squared minus 1 squared times u times du. And this, when we write du, we have to say it's equal to secant theta, tan theta, d theta. I forgot that. So now we have something we know we can work with. And we are going to just erase this top line so we can make room. Well, what is this integral of u squared minus 1 squared times u? Well, this is going to be equal to the integral of u to the 4th minus 2u squared plus 1 times u du. Well, we just distribute that u, so then this would be u to the 5th. This would be u cubed. This would be u, just u, and that u would go away. And then we would have, well, I'm going to erase this line. Well, then we know how to do this integration really easily. It's just power rule. Or I guess reverse power rule, if you will, because power rule kind of implies derivatives. So, we have that, and we just do the derivation, or integration, and we get, well, this is just u to the 6th over 6 minus 2u to the 4th over 4 plus u squared over 2, and we would have that this is plus c, and then we just plug in whatever we needed to plug in based off our u's. Well, what was our u? Our u was secant theta. So then we just plug in secant theta, and this would be secant to the 6th theta over 6 minus 1 secant to the 4th theta over 2, because 2 and 4 cancel, and then we have plus secant squared theta over 2 plus c. So we can see same sort of deal for sines and cosines. We just have to choose one, replace, go from there. So let's jump into the rules. Into our rules, we have two rules similar to our sines and cosines. Here, if n is equal to 2k, i.e. we are looking at our secant, if we have the integral of tan to the mx times secant to the nx dx, if n equals 2k, factor out a secant squared such that secant x now equals 2k minus 2x, which will then be equal to 1 plus tan squared x to the k minus 1 power, and we can see what that looks like. Well, this would equal the integral of tan to the mx times 1 plus tan squared x to the k minus 1 power times secant squared x dx. And for your u substitution, let u equal to tan x. Why do we do this? Well, the derivative, i.e. du of tan x, is going to be equal to secant squared dx. So, we see secant squared dx on the outside. We can do a perfect u substitution. Now, if our m, or the power related to our tangent, is odd, i.e. m is equal to 2k plus 1, save a factor of secant x and tangent x. Why do we do this? Well, the derivative of secant x is going to be secant x tan x, so for our u substitution, and then we can just change the integral. Now it's the integral of tan x to the 2k plus 1 x times secant to the n x dx, which is equal to the integral of tan to the 2kx times secant to the n minus 1 x, because we had to save a power of secant, save a factor of secant, and then times secant x tan x dx. Well, this is now equal to the integral of secant squared x minus 1 to the k, because that's what tan turns into. And then we do times secant to the n minus 1x times secant x tan x dx. And as I said, we use u equal to secant x. So these are the rules for our secants and tangents. For cotangents and cosecants, essentially it's the exact same thing, except we use cotangents and cosecants, and tangent corresponds to cotangent, secant corresponds to cosecant. What if we just have a normal tan x or a normal secant x? Well, we know the derivatives quite well. Obviously, I've told you what they are in this video, and we've done derivative videos in the past. But we've never done the integral of tangent or secant. Well, the integral of tangent dx is going to be equal to ln of the absolute value of secant x plus c, and the integral of secant x dx is equal to ln, natural log, of the absolute value of secant x plus tangent x plus c, right? And so I'm not going to do the derivations, I'm not going to do the proof, if you will, but I challenge you to do them now. And how you would do this? Well, just take the derivative of this and show that it's equal to tangent. We have one more set of rules, and then we will go into our practice problems. We run into our last three identities for this video that we need to know, and we have, if we have sine mx times cosine nx, or sine mx times sine nx, or cosine mx times cosine nx, well, when would we even need these? Well, if we had the integral for, let's say, sine of 5x times cosine of 3x, we would not be able to do a solid u substitution. But we have these identities. Well, we have this sine mx times cosine nx is going to be equal to 1/2 sine mx minus nx plus sine mx plus nx. Alright, now if we had double signs, we had sine mx times sine nx, that is equal to 1/2 cosine mx minus nx minus cosine mx plus nx. Finally, if we had double cosine, i.e. cosine mx times cosine nx, this is going to be equal to 1/2 cosine mx minus nx plus cosine mx plus nx. And so we have these in case, and so technically this doesn't have to be an m and this mx, and this doesn't have to be an nx. That's what a lot of the problems are going to be, so I wrote them out like that. But technically you could just have anything inside your sine and cosine functions. For example, this could be like an x squared, or that could be like a 3x squared, and then that could be a 2x or something. It doesn't matter. You could have another function inside as long as there is a constant out in front. You can combine them. So that is all I wanted to cover for the lecture portion of today. We are going to transition to some practice problems. Fucking really? Okay, well, my neighbors just turned on the shower, and there's only going to be solid light in this room for another, like, 20 minutes, so I'm very sorry if you can hear the fucking noise, but we're doing number 27, and so if we had the integral of tan cubed x times secant x dx, and, well, what do? Well, we see tan is odd. Okay, that means we take out a tangent, and we rewrite this as the integral of tan squared x times secant x tan x dx. And then, well, what do? Well, we know that sine squared plus cosine squared equals secant squared x. So then if we divide by cosine on all the sides, we get tangent squared x plus 1 is equal to secant squared x. So then tangent squared x is just going to be equal to secant squared x minus 1, and then this would be secant x tan x dx, and so, well, this is going to be equal to the integral of secant squared x times secant x, or wait, I'll do that. So then we have we have the integral of secant squared x minus 1 times secant tan x. Well, we know that u equals secant x and du equals secant x tan x. Well, then this is going to be equal to u squared minus 1, the integral times du, which is just going to be equal to u squared, or u cubed, over 3 minus, well, the integral of 1 is just going to be u, and then plus c, and then we just have to fill in our u's, and we can say that the integral of tan cubed x times secant x dx is going to be equal to u cubed over 3 minus, or what, u cubed, what, plug in secant, so secant cubed x minus secant secant x plus c. And that is how we do 27. Now our final question, we're going to be doing number 41 from our textbook. If we have the integral of sine 8x times cosine 5x dx, how do we even approach this? Well, we learned right at the very end of the lecture portion that sine mx times cosine nx is equal to 1/2 sine of mx minus nx plus sine of mx plus nx. Well, so then we can just apply that rule with 8x and 5x. Well, this is going to be equal to the integral of 1/2. Let's say 1/2 of the integral, because we can bring our constant out in the first place, and then that's sine of 8x minus 5x plus sine of 8x plus 5x dx. And then, well, what do? Well, this is just 1/2 integral sine of 3x plus sine 13x dx. And then this is really easy to do. This is going to be 1/2. Well, the integral of sine is negative cosine, so then this would be negative cosine of 3x over 3, because we have to account for chain rule when we do derivatives and the integrals, minus cosine of 13x over 13 plus c, and then we could just rewrite this as negative cosine 3x over 6 minus cosine 13x over 13 plus c. So that is everything I wanted to cover in today's lecture. Thank you all for watching. As always, my name was Logan. Have a great day.